Hi, Sam. Thank you. I want to, first of all, to start by thanking Wien and the president for inviting me at this great conference. I learned a lot today in the morning. It was really interesting. Now, let me go to show you a couple of fresh results from James Webb, and I will build on the excellent review that Sandro just did to go quickly on the motivation, but I think it is. Let me try to explain the overarching goals I think we have in mind when we do search and study the high redshift universe. And when I speak a high redshift, I refer to redshift greater than 10. One, as Sandro mentioned, the physical conditions were completely different. The universe, first of all, was much denser. There was very low metallicity. The CMB was warmer. There was no ultraviolet background permeating the universe. And so stars, as a result, were significantly different, low metallicity, etc. So the physical conditions of the objects at that time were completely different. So we are entering really in a new range of physical laws. There is also the possibility that at very early time, we are sensitive to some new physics. So to some physical mechanism outside the standard dark matter model, which we may have had an impact at very high redshift and not at low redshift. Just as an example, you may have a population of primordial black holes, and so at very high redshift, this may trigger additional star formation activity, and so as a result, there are speculations that beyond redshift 10, the star formation is higher because of these additional seeds. Or you may have extended different models for dark energy, for instance, an additional scalar field in this case, which boosts the number of dark matter halos. And so you have more galaxies just because you have more dark matter halos. And again, this is sensitive, has an impact only at very high redshift. There are other options, for instance, work dark matter models predict the opposite. You have less galaxies because you cancel the smaller. So, of course, before claiming for evidence of new physics, we need to have a clear and robust understanding of the ordinary physics, what baryons usually. And so this was the motivation. Now, in the spirit of this academy, I want to briefly mention, and also remembering the talk by Marcia about my history on James Webb started only 2 years ago when the first data were released. I was part of this ERS team. And I remember the excitement when on July 14, the first data of GLASS were released. And it started really an incredible race. In the center, you can see the image of the screen. There were 30 people connected, looking at the data when they were flowing in. And we were spread over 3 continents. And it started the race working 24 hours a day over 3 continents, working hard. And as you may see, only in 5 days, we submitted the paper, which I think is remarkable. And it was not entirely wrong, which is already a success to me. And there were, was a brand new instrument for all of us. We were relying on pipelines, and I will not say anything more on this. And at the same time, there was another team, Sandro was part of it, who was also working on the same data. We landed on the archive separated by 3 minutes only, so which gives you an idea of the tension and the competition that was at the time. And the reason for we were so interested and excited is that we were sort of depressed at the beginning because we were expecting in our deep imaging obtained with GLASS, we were expecting on average 0.1 candidates beyond redshift based on the extrapolations we had at the time. So we had already written a paper saying, sorry, we didn't find anything, but it was expected. And instead, we found 2 very bright galaxies, very convincing, the same, of course, the other team, which are shown there. They have a very, in the inset, you see the photometric redshift is very robustly limited to redshift 10.6 in one case and 12.2 in the other case. And so, of course, you may claim that the statistics 2 objects out is not really a great statistics, but this is clearly now an established result. As you know, as Sandro mentioned, there are now a lot of public fields, a much wider area, stretching down easily to magnitude 28 or 29. So you may have we have already detected a population of galaxies beyond redshift 10 in these fields. And the result is that the number of galaxies, so the first thing we do is just we count galaxies as a function of magnitude. So this is a luminosity function, number of galaxies as a function of the absolute UV magnitude. The number of galaxies that are detected in this field is definitely above the expectations of extrapolations of earlier data. You may see on the left, the points are significantly above the extrapolation at redshift 11 and even more at redshift 14. And also on the right of theoretical models. So all the little gray lines on the right were predictions of theoretical models, which all fell short of predicting the right number. Now, of course, these days there are new ideas coming in, so there are a few models which are trying to reproduce the numbers, but with a number of assumptions and implications on the properties of these galaxies which are not tested at the moment. So this has been really one of the great surprises that the very early observations which have provided us. Now, explanation, I'm sure we can make a conference on possible explanations. There is a large number of options, and I don't want to drive you through all of them. Of course, refer to baryon physics. Some of them has already been mentioned. So you may have bursty star formation, you may have a completely different IMF, and so on and so forth. But so far, I have not seen a self-consistent theoretical model which convincingly produced these findings, and at the same time, the nature of these galaxies. But again, there are other two possibilities. One is AGN, so these galaxies are brighter because there are AGNs inside, and GN-Z11 has just been shown to host one of these objects. Or, as I mentioned, the possibility of new physics, and there are a number of options in alternative cosmologies dealing with. So to understand these, of course, you have to go beyond counting galaxies and start to get the physics of these objects. And this was the motivation of a program which is ongoing, where we went on the glass region, especially, which is, as you may see here, we have been lucky. This is the field with the highest density of bright sources beyond redshift 10. So there are several of them, and in particular, the two guys I've shown you before. And I will now focus on, so the program is halfway. So we have the first half of the data on GHZ2. As already shown by Sandro, it's one of the brightest, is the second brightest galaxy beyond redshift 10 with spectroscopic redshift, at least until 10 minutes ago when Sandro showed that there is one at redshift 14. But it's clearly an outlier in the distribution. And the spectrum, so we got the spectrum with NIRSpec, and also in parallel, another program by Jorge Zavala with MIRI. And this is the spectra that we got. These are the spectra that we got. On the right, you see, on the left, you see NIRSpec, and on the right, you see the MIRI detection. So MIRI is astonishing. This is to my knowledge, is the highest, is the most distant galaxy ever detected with MIRI. You see the complex H beta and oxygen 3 and nitrogen 2 and H alpha blended 2. And on the right, on the left, you see the NIRSpec spectrum with blooming emission lines. Right at the redshift 12.3, which is very close to the photometric redshift. So these are good news. Of course, now the question, if you look at the spectrum, the first time I said, okay, I'm an old astronomer, so I said that's must be an AGN. Unfortunately, the situation is more complex. You see strong emission lines in carbon-4, carbon-3, and oxygen. So situation is more complex. So let's first look at the properties of this galaxy, which is at those redshifts has a pretty high stellar mass. So we do a fitting, we fit the continuum without the emission lines, and we get these parameters. Stellar mass is depends on models, but is definitely above 10 to the 8 solar masses, probably closer to 10 to the 9. Staff emission rate of the order of 10 per year, and so on. A very low metallicity, and ambiguously we fix the metallicity below 0.1 solar. The size is very small, is of the order of 80, maybe 100 parsec, which makes the stellar density very high. So it's a stellar density typical of bound star clusters. So we are already, we're in a very dense environment. Now, if you look, if you want to determine whether this is an AGN or a star-forming galaxy, the physical conditions are so different. Having carbon-4 in emission is not enough to claim it's an AGN. Again, the ionization can be completely different. So you have to go through models fitting, playing with emission, with the ratio between emission lines and comparing with models. So in red, you see the AGN model, and in blue, the star-forming models. And the orange point, which is this galaxy, sits exactly in the same, in the middle of the, so it's very difficult based on these, and given the uncertainties in these kind of models to determine which is which. If you look at the equivalent widths, again, they look more convincingly typical of AGN. They are very high, as we find typically in AGN only, but we don't detect the high ionization lines like neon 4, which are the smoking gun of an AGN. So I think the jury is still out, and we definitely need deeper data and higher resolution spectra to get the faintest. However, we can establish a number of properties of this object. The first, as I said, the metallicity, if you play not only with the continuum, but with the lines, is unambiguously low, whatever the nature, even in case of AGN or star forming. The ionization factor, if it is a star-forming galaxy, is very large, so it's of the order of minus 1.8, which again points to a very high ionization rate, a very high density of the ionizing stars in the galaxy. It's significantly far away from the typical mass metallicity and fundamental metallicity relation established even at nearly those redshifts. So it's clearly in a phase, in a very unusual phase. And I'm a bit, I hope you will not blame me. I show this line, we're working hard to understand and assess its reliability. If this line will be confirmed with deeper observations, it might indicate that this galaxy is enhanced in nitrogen, the other 4 times the solar one, which is what was found by Roberto in GNZ11 and is typical of globular clusters. So it may be tempting to speculate that this, if confirmed, this galaxy is forming a generation of globular clusters and so just to conclude, so it is intriguing to see that the 2 brightest sources are extreme sources. One is definitely an AGM, the other may also be. In any case, they have ionization, high density, low metallicity, and possibly supersolar and/or oxygen. And who knows? So we might speculate at this point that they might represent a short phase in galaxy evolution, which in the model is clearly not implemented. In the last minute, just to show you that, as I mentioned, there is an overdensity, an apparent overdensity of galaxies. We don't know if it is physical or not. In the first data, we find that these 2 galaxies, which are really very nearby, are actually at the very same redshift. So it looks like it is at a redshift 7.5. It really looks like it is a physical pair at this redshift. And interestingly, the second one, the lower one, has a hint of a Lyman alpha, which may indicate that they have started to ionize the universe and create a bubble there in the dense region. And so stay tuned for the final results of the survey, and I will leave the take-home messages here, and I'll stop.